Today we are going to explore one of the most fascinating and forgotten stories of medieval metallurgy. Bog iron, a natural resource that entire communities harvested as if it were an agricultural crop. Before continuing with the video, remember to subscribe to the channel for more documentary narratives like this one. Imagine for a moment a soaked landscape in northern Europe, where the morning mist hangs over dark waters and peat accumulates over centuries. Feet sink into the reddish mud, and the air carries a characteristic odor of decomposing organic matter. To the untrained eye, this scenery is nothing more than an obstacle to be bypassed. However, more than 1,000 years ago, a medieval blacksmith would have immediately recognized what lay hidden in that fetid mud. He would have knelt and begun to dig, because within that clay there was iron. Not an ore buried by geological forces or extracted from deep tunnels, but iron that grew there, deposited grain by grain over decades by bacteria and groundwater, waiting to be harvested like a crop. This is the story of how medieval communities transformed swamp mud into metal, and how this metal possessed a property that modern steel still struggles to achieve. To understand bog iron, it is first necessary to understand what happens at the chemical level inside a peat bog. Iron dissolves into groundwater from surrounding rocks and soils. In the oxygen-poor environment of the underground, it remains in a soluble form called ferrous iron. Essentially invisible, dissolved in the water like salt in seawater. But when this iron-rich water rises to the surface through springs or seeps into wetlands, something fundamental changes. It encounters oxygen. The ferrous iron oxidizes into ferric iron, which is insoluble. It precipitates out of the water as solid particles of iron, oxyhydroxide, primarily a mineral called goethite. These particles accumulate in the peat, in the sediments around plant roots, forming layers of porous, brittle material with a rust-orange coloration. This process is not just chemistry, it is also biology. Specific bacteria, particularly species like Thiobacillus ferrooxidans, act as catalysts in this transformation. They oxidize the iron enzymatically, concentrating it as part of their life cycle. And there is a sign that reveals the presence of these bacteria without the need for any equipment. They leave a distinctive film on the surface of stagnant waters, a film that looks like oil, but which actually consists of a gelatinous precipitate of iron hydroxide. If someone touches it, it fragments like thin glass instead of flowing like oil. Medieval iron hunters knew this sign well. That iridescent film was an unmistakable marker. There is iron here. The truly remarkable characteristic of bog iron lies in its capacity for regeneration. Economically useful deposits can replenish themselves in approximately 20 years after harvesting. The same bog could be exploited once per generation. The surface peat was removed, the iron nodules were extracted, the peat was replaced, and one waited. 2 decades later, the bacteria and groundwater would have deposited a new metallic crop. This makes bog iron one of the only renewable metallic ores in human history, a resource that regenerated naturally while communities utilized it. Medieval communities across northern Europe organized entire economies around this resource. In Scandinavia and Finland, bog iron dominated iron production approximately between the years 500 and 1300 of the Common Era, a period of 8 centuries of continuous use. In Iceland, large-scale production facilities known as iron farms operated specifically to harvest and smelt bog ore. Smaller rural properties also practiced this activity, producing enough iron just for self-sufficiency. In Hungary, more than 300 smelting workshops from the early Middle Ages have been excavated by archaeologists, many of them processing local ore from peat bogs. The process of transforming swamp mud into usable iron followed a sequence that was fundamentally the same in all these regions. Although there was no contact between them, the universality of the method suggests it was not invented once and then spread. It was discovered independently multiple times because the logic of the process is almost self-evident once the material is understood. The first stage consisted of collection. Medieval ironworkers identified bog ore deposits by reading the landscape. They looked for withered grass, damp ground with specific moisture-loving vegetation, and reddish-brown discoloration in nearby waters. Once a deposit was located, they used wooden or metal probes, pushing rods into the soft soil to detect larger concentrations of ore beneath the surface. Then they cut layers of peat with specific knives and extracted the ore manually. Some deposits contained pea-sized nodules scattered through the peat. Others formed larger crusts and plates. The second stage was roasting. The collected ore was wet, often saturated with swamp water. Before it could enter a furnace, it needed to be dried and partially purified. The workers arranged the raw ore on a bed of firewood and lit it. The heat, reaching approximately 600 to 800 degrees Celsius, drove out moisture and burned off volatile impurities, particularly sulfur. Excess sulfur makes iron impossible to work with, causing it to become brittle and crack during forging. Roasting also made the ore more porous and easier to crush into smaller fragments, which improved the flow of gases during smelting. The third stage was the smelting itself. Medieval smelters built direct reduction furnaces, bloomeries, with local clay, typically conical structures, 70 to 100 centimeters high, with an internal diameter of 30 to 40 centimeters. The furnace was loaded in alternating layers of charcoal and crushed roasted ore, in a ratio of approximately 1:1 by weight, adding 7 to 15 kilograms of ore incrementally over 2 to 4 hours. Air was supplied through a clay tube called a tuyere, connected to hand-operated bellows. The smelting temperature reached between 1100 and 1300 degrees Celsius. This point is fundamental to understanding the process. The melting point of pure iron is 1538 degrees Celsius. Medieval furnaces never reached this temperature. The iron never became liquid. Instead, at the lower temperatures of the bloomery furnaces, the iron oxide in the ore was chemically reduced by the carbon monoxide coming from the burning charcoal. The oxygen was removed, leaving behind solid particles of metallic iron that welded to each other, forming a spongy, porous mass called a bloom. Meanwhile, the unwanted material, silica, alumina, various impurities, melted into liquid slag that flowed down and out of the furnace. The yield was modest. A bloomery furnace typically converted only 10 to 20% of the iron contained in the ore into usable bloom. The rest was lost in the slag. But the bloom that emerged was real iron, ready for the forge. The fourth stage was consolidation. The bloom came out of the furnace filled with trapped slag, charcoal fragments, and voids. It needed to be hammered repeatedly, while hot, to expel impurities and compress the metal into a solid, workable ingot. This was arduous physical labor. Each blow expelled pockets of liquid slag and welded the iron grains more firmly. The result was wrought iron, a low-carbon iron that could be shaped into tools, nails, hinges, knives, and weapons. This is where the story becomes genuinely interesting from a materials science perspective. Modern industry treats phosphorus in steel as a contaminant in concentrations above approximately 0.04%. Phosphorus causes what metallurgists call cold shortness, a form of weakening that makes steel crack under impact, especially at low temperatures. Every modern steel specification sets strict upper limits for phosphorus content. However, bog iron ore is naturally rich in phosphorus. Chemical analyses of bog ores from Somogy County in Hungary, conducted at the Budapest University of Technology and Economics, found concentrations of phosphorus pentoxide between 3 and nearly 5% by weight in the raw ore. This phosphorus transfers to the iron bloom during smelting. The resulting metal, which researchers call phosphoric iron, typically contains between 0.5 and 1.5% phosphorus by weight. In modern terms, this is an absurdly high phosphorus content. No modern steel mill would produce it intentionally, and yet archaeometric studies across Europe have confirmed that phosphoric iron was not a defect. It was deliberately used throughout the entire medieval period. Why? Because phosphorus does two things that medieval blacksmiths discovered empirically centuries before anyone understood the chemistry involved. First, phosphorus increases hardness. A phosphoric iron blade holds an edge better than pure wrought iron. Medieval knife makers exploited this by using phosphoric iron specifically for the cutting edges. Second, And more importantly for our story, phosphorus increases corrosion resistance. Iron made from bog ore, with its residual phosphorus content and often with residual silicates that form a glassy coating on the surface, resists atmospheric rust significantly better than common wrought iron or modern mild steel. This was not theoretical knowledge for medieval craftsmen. They could see it with their own eyes. The most dramatic demonstration was in pattern-welded sword blades. Between the 5th and 14th centuries, European swordsmiths created blades by forging together, welding alternating strips of different types of iron, then twisting and grinding them to produce serpentine patterns on the blade's surface. Phosphoric iron from bog ore was used as one of the contrasting metals precisely because it corroded at a different rate than the layers of common iron and steel. When the blade was etched with mild acid, the phosphoric iron remained bright, while the other metals darkened, creating a striking visual contrast. The pattern welding technique depended on the corrosion resistance of bog iron to make the decoration visible. Researchers from the Budapest University of Technology confirmed this through smelting experiments. When bog iron ore with high phosphorus content was smelted in reconstructions of medieval furnaces, the resulting blooms contained phosphoric iron with microstructures that match those found in archaeological sword blades and knife edges dating from the 8th to the 14th century. The Vikings took bog iron to places where no European had smelted iron before. Around the year 1021 of the Common Era, Norse explorers established a settlement in what is now L'Anse aux Meadows, at the northern tip of the island of Newfoundland, in Canada. The site consisted of 8 peat-covered wooden structures, including 3 dwellings, a forge and 4 workshops. Archaeologists recovered 98 nail fragments and numerous rivets from the site, along with 15 kilograms of slag. The analysis of the slag confirmed that it matched the iron of the nails. The Norse had located a local peat bog, harvested bog iron from it, smelted it on site, and forged nails for ship repair. This was the first iron production in North America, and it was carried out with bog iron. A single Norse longship required approximately 7,000 nails, forged from about 400 kilograms of finished iron. Producing that amount of iron from bog ore meant a blacksmith would need to process approximately 30 tons of raw ore. Historians have argued that iron was actually a prerequisite for Viking settlements. They proposed that the Norse, knowing their ships would need repairs, actively sought locations where bog iron was available. The settlement at L'Anse aux Meadows was positioned immediately adjacent to a peat bog. This was no coincidence. By the time the Norse arrived in Newfoundland, Scandinavian communities had been smelting bog iron for nearly 1,500 years. The knowledge was so widespread that even relatively inexperienced workers could produce usable iron. The analysis of the slag from L'Anse aux Meadows showed that significantly more iron could have been extracted from the ore than actually was, suggesting that the workers there were competent but not expert smelters. This supports an important point. Bog iron smelting was common knowledge, not a trade secret restricted to masters. In Russia, bog ore remained the primary source of iron until the 16th century, when deposits in the Ural Mountains became accessible. In colonial North America, bog iron was extensively harvested along the East Coast. During the American Revolution, cannonballs were cast from bog iron for the colonial forces. The first known iron mines in North America, reportedly in operation around 1578 in St. John's, Newfoundland, were bog iron operations. The Saugus Iron Works in Massachusetts, established in 1646, processed local bog ore. The Nassawango Iron Furnace near Snow Hill, Maryland, operated commercially from approximately 1825 to 1850, processing bog iron from nearby swamps. Throughout central and southern New Jersey, bog iron was smelted and forged into tools, and structural wrought iron railings specifically valued for their natural rust resistance. Many of these railings still remain on buildings, in Trenton and Camden, still intact, still supporting staircases and balconies. Meanwhile, modern mild steel exposed to the same coastal air begins to corrode within months. So what happened? Why did we stop? The answer is not that we found something better in every respect. The answer is that we found something cheaper and faster. The shift began with the development of coke-fired blast furnaces in the 18th century. These furnaces could process ore extracted from mines, particularly hematite and magnetite, at temperatures and volumes vastly superior to what bloomery furnaces could handle. A blast furnace produces pig iron in liquid form that can be poured into molds. Production scaled from kilograms per day to tons per day. The economics were overwhelming, but there was a trade-off. Blast furnace iron and the steels derived from it have fundamentally different compositions from bog iron produced in bloomeries. The phosphorus that gave bog iron its corrosion resistance was now considered a contaminant to be removed. The silicate inclusions that formed a protective glassy layer in wrought iron were eliminated. The new steel was stronger, more uniform, more available, and vastly cheaper. It was also much more vulnerable to rust. And so we entered the modern era of metallic corrosion. According to the Federal Highway Administration and NACE International, rust costs the United States $276 billion every year. This represents 3.1% of the entire gross domestic product spent fighting a problem that medieval blacksmiths partially solved with swamp mud. The global cost of corrosion is estimated at $2.5 trillion annually, approximately 3.4% of the world's gross domestic product. We did not solve the problem of rust. We scaled it. Bridges collapsing, water pipes bursting, reinforced concrete disintegrating. The United States alone experiences approximately 240,000 water main breaks per year, most caused by corrosion. There is an irony in the modern approach to corrosion that a medieval blacksmith would find baffling. We produce steel that rusts easily, then spend enormous sums applying coatings, galvanization, paint, cathodic protection, and chemical treatments to stop it from rusting. We engineer solutions for a problem that exists in part because we engineered the corrosion resistance out of the metal in the first place. Modern weathering steel, sold under trade names like Corten, attempts to mimic part of what bog iron does naturally. It uses a mixture of elements including manganese, nickel, silicon, and chromium to form a stable layer of rust that protects the underlying metal. It is a good material, but it is worth noting that medieval bog iron achieved a similar effect using nothing more than the natural chemistry of a swamp. The experimental archaeology community has kept the knowledge alive. In Somogy, Hungary, an annual 5-day international iron smelting camp teaches participants the complete medieval process, from charcoal burning to ore collection, through bloomery smelting to the forging of finished products. The Hurstwick Research Group in New England conducted multi-year experimental archaeology projects replicating Viking-age iron smelting in Iceland, successfully producing high-quality iron from locally obtained bog ore and refuting the long-held belief that Icelandic bog iron was of low quality. These experiments confirmed something important. The process works. It is labor-intensive and slow, but the iron it produces is real, functional, and in some measurable ways superior to modern alternatives for applications where corrosion resistance matters more than volume. So could someone today actually do this? Could a person harvest bog iron and smelt it? In principle, yes, bog iron deposits still exist throughout northern Europe, Russia, Canada, and parts of the northern United States. The iridescent bacterial film on swamp water still marks potential deposits. The process requires no electricity, no modern chemicals. One needs clay to build a furnace, charcoal for fuel, bellows for air, and patience. In practice, there are legal and environmental considerations. Many wetlands are now protected habitats. Collecting ore from a protected bog would violate environmental regulations in most countries. And setting up a charcoal burning operation produces significant smoke. But the knowledge itself is accessible. Experimental archaeology groups publish detailed documentation of their smelting methods. The journal IGSARC, an international publication for experimental archaeology, includes step-by-step reconstructions of medieval smelting processes. The Hurstwick Group's research on Icelandic iron smelting is publicly available. For those interested in self-sufficiency, the conclusion is this: smelting iron from bog ore is one of the very few metalworking technologies that can be performed entirely with hand tools and natural materials. No grid power, no industrial supply chain, just knowledge, labor, and a swamp. More than 1,000 years ago, a Norse explorer landed on a rocky coast in Newfoundland. His ship needed nails. He found a peat bog, recognized the signs of iron, built a clay furnace, burned charcoal from local wood, and produced the metal he needed. The nails he forged were recovered by archaeologists a millennium later. They had survived 1,000 years in acidic, waterlogged soil. Today, a standard galvanized nail loses its protective zinc coating within 15 to 20 years in a marine environment. An untreated mild steel nail can rust away completely in less than a decade. The Viking nail is in a museum. The modern nail is in a landfill. We have not advanced beyond medieval metallurgy in every respect. In some very specific and measurable ways, we chose speed and volume over durability. Bog iron was slow to make, limited in quantity, and required intimate knowledge of local landscapes. But it lasted, and a $276 billion corrosion bill that we pay every year suggests that lasting is worth more than we have given it credit for. In the swamps of northern Europe, in the peat bogs of Scandinavia, in the wetlands from Russia to Canada, iron still grows. Grain by grain, year after year, bacteria and groundwater continue depositing this renewable ore. The iridescent film still floats on the surface of stagnant waters, marking deposits for anyone who knows how to read the signs. The knowledge survives in experimental archaeology communities, in academic papers, and in 1,000-year-old nail fragments preserved in museum cases. Perhaps the most profound lesson of bog iron is not about metallurgy. It is about the choices we make when scale becomes possible. Medieval blacksmiths worked within the limitations of their materials and processes. They produced metal slowly, in small quantities, with deep knowledge of every step. The metal they created carried the chemical characteristics of its origin, and those characteristics, treated as defects by modern industry, conferred properties that we still try to replicate artificially. When blast furnaces made mass production possible, the priority shifted. Volume replaced quality in certain respects. Uniformity replaced beneficial quirks. Phosphorus was removed because it caused problems in some applications, even if it was advantageous in others. And now we spend a significant portion of our collective wealth fighting the consequences of that choice. This is not an argument to abandon modern metallurgy. The steels we produce today make possible structures and technologies that medieval blacksmiths could never imagine. But it is a reminder that progress does not always mean improvement in every dimension. Sometimes, by gaining in one area, we lose in another. Bog iron represents a way of thinking about resources that is fundamentally different from our modern approach. It was a renewable resource in an era when most people did not even conceive of such a category. It was a process that required patience measured in decades, not minutes. It was a technology that worked with nature rather than against it, harnessing natural biological and chemical processes. The story of bog iron is, ultimately, a story about what we value. Medieval blacksmiths valued durability because they had no choice. Their metal had to last, because producing it was too much work to waste. We value speed and scale because we can. The next time you see a reddish stain in a stream or an iridescent film on the surface of stagnant water, remember that you are looking at the same sign that guided medieval blacksmiths to their ore deposits. The iron is still there, growing slowly, waiting for whoever has the knowledge and the patience to harvest it. If you learned something new from this video, consider subscribing to the channel. Every week we explore forgotten medieval knowledge like this, stories of technologies that our ancestors mastered and that still have much to teach us. Leave a comment telling us which medieval technique you would like us to investigate next. Perhaps it will be the next story we tell together. And if this content was valuable to you, share it with someone who also appreciates these journeys through the past. Thank you for watching, and we'll see you in the next episode.